To be a little clearer about what we mean by the limit of a sequence, I sort of wrote up the intuitive definition. A sequence has the limit L, and we'll write that the same way as we usually do. The limit as n goes to infinity equals L. If we can make all the ANs as close as we want to L by taking n sufficiently large. In other words, we're going far enough out on the sequence. And if that happens, we say the sequence converges, just like a regular limit in x, and otherwise we say the sequence diverges. If you think about this, this isn't radically different than thinking about the limit of f of x as x goes to infinity. The only difference is that we've got an integer n instead of real number x. So that leads directly to this little theorem, which says if I think about a function as a function of x and it's going to go to the limit L as x goes to infinity, then that's going to also happen with this corresponding sequence. What that means, basically, is that pretty much however we took limits back in the beginning of this, beginning of this book, right, in Calc 1, as we took the limit as we go off to infinity, we can use the same stuff here, as long as it makes sense to write it as a function like that. The only time when it really doesn't is when you have something, with a minus 1 to the n. As I said before, a minus 1 to the x doesn't make sense, so we can't use it in that case. But for most cases, it's fine just to use the techniques that we used for limits at infinity. So, for example, if I have something like this, you remember we can multiply by the top and bottom power. Of course, the top and bottom, or the biggest power that is on the top or the bottom, right, is what I meant to say. So, but it's actually, in this case, it's the same, top and bottom. It's square root of n squared. So we're multiplying top and bottom by 1 over n outside the square root. But of course, when I take that into the square root, it's going to be n squared. So I end up with 1 over n squared plus 4, since those n squares cancel out. And then I have 1 over n squared plus 1. This is a continuous function. I can take the limit inside. This one goes to 0. This one goes to 0. I have the square root of 4, which is 2. For these sequences, we're always taking n out to positive infinity, so we don't have to worry about any negative square root business or anything, because our n's are positive infinity. Okay? Something like this. Okay, there's ways to do this without L'Hopital's rule, but L'Hopital's rule is probably the easiest way to do this, right? Because you can see it's natural log, it's infinity over infinity. Technically, you can't use L'Hopital's rule with an n, right? Because these are discrete dots, how you can take the derivative. So what you do if you're going to use L'Hopital's rule is exactly what this little theorem said. We just write it with an x, okay? So if I write it with an x, let me consider what's going to happen in the continuous case. If I get a finite limit here, I know I get a finite limit here. Okay, now if I use L'Hopital's rule, I take the derivative of the top and the derivative of the bottom. The derivative of the top is just 1 over x. The derivative of the bottom is 1 over 2x. Remember, I have to take the derivative of the inside, so it's 2x times 2. Eventually, I just 1 over x over 1 over x. So this is the limit as x goes to infinity of 1, which is 1. Okay, so if the function with x does it, the discrete version does it too. So this has to be equal to 1 by the calculation below. Okay. However, and I believe we sort of had one of these in the previous video, if I have something that does this, okay, so let's look at this. So this, I've got an issue with this minus 1 to the n. So sort of mentally, let's figure out what's going on here. If I just look at the positive part, this is going to go to 3/4. So this is very similar to the other example that we had, where it was going to be bouncing back and forth. Once I put this, I've got a situation where my sequence is bouncing back and forth between positive and negative values. So I've got this possibility. So if what happened, or what would happen if I had this? If I have this, I can do, in an easy place, right? Because it's just very standard, right? We know that this one goes by the same thing, same technique, right? We are going to have 3 plus 5 over n squared, 4 minus 7 over n squared. These guys go to 0. This is equal to 3/4. I do that here, this is not going to work out entirely in the same way. Well, I could do that, though. I could do that. I would end up with limit as n goes to infinity minus 1 to the n times 3/4 if I do the exact same calculation. Now, this limit, you can see, does not exist, right? Well, really, I should write it this way, right? I should write it as 3 plus 5 over n squared, 4 minus 7 over n squared. Okay, this is going to go to the two places, right? It's going to go to either negative 3/4 or positive 3/4, depending on the value of n, right? So this would approach negative 3/4 for n odd, and positive 3/4 for the evens, so limit doesn't exist. So that's kind of the way you want to approach these ones. Now, let's do one more very related example. Just because it has a minus 1 to the n does not mean, right, that it's necessarily going to not exist. So let's just change this up very slightly and get rid of that. So here, what I have is I have some mess, right? But the power in the bottom is bigger. So if I look at the corresponding just these positive terms, right? Well, positive after n equals 1. If I look at this, I do the same thing. I'm still going to divide top and bottom by the highest power, which is n squared. Remember, that's how we deal with these limits. But then I'm going to have 3 over n plus 5 over n squared. And this is going to be 4 minus 7 over n squared. So everything goes to 0 here except for this 4. So I end up with 0 over 4, or 0. So this guy goes to 0. And now if I were to do the same thing with the minus 1 to the n, I end up with minus 1 to the n times 0, which is 0, right? Because everything like 0 is 0. So in the special case where your terms are going to 0, the fact that they're switching signs doesn't matter. Okay, and you can see that by even drawing. If you go to the GeoGebra worksheet, you can draw this and you can see that. And you can see how it bounces back and forth over the axis, but as n gets bigger, it's going to go to 0. So I'm just going to write this the same way as we did before. So if I do the same thing, I'm going to get 3 over n plus 5 over n squared over 4 minus 7 over n squared. Everything goes to 0. So this is going to be 0 for all n. Right? Okay.